This is the reinforce algorithm. You'll find it in the reinforcement learning book by Sutton and Barto. Maybe you've seen it, maybe you've read it, but have you implemented it? Turns out when you go from theory to practice, it's not so straightforward. But let us begin at the beginning. So in reinforcement learning, we have this agent that interacts with the environment. You can think of the environment as like a black box. It processes some action and it produces the next state and some sort of reward. The problem we have is that environment is not differentiable, because environment might be doing some very complicated things for which we don't have actual expression or function. We are not able to compute the derivative of it. And if we can't compute the derivative of our environment, then we can't backpropagate through it. Why is this a problem? Well, you can think of an agent as having some sort of neural network inside of it with some weights. And we need to update these weights. And in order to update these weights, we need to backprop through our neural network. So we need the gradient at the output of this neural network. So environment is like a black box. It takes an action, it does something, and it outputs a state and a reward. So instead of using the output of our environment and backpropagating through it, and then backpropagating through our agent to update the weights of this neural network, we must find some other ways of updating these weights instead. Imagine you have a dog that does something that the owner likes. Then the owner will give the dog a treat, and the dog will tend to remember that this action leads to a treat and will do that action more often. We can also draw this the same way we drew our environment before to see how the learning happens here. And as we can see, the dog uses the treat to reinforce those actions that the owner considers good. In other words, if the dog selects an action that results in good outcome, well, then it should take that action more often in the future. For example, if the distribution of a possible action is as follows, and one of these actions turns out to lead to a good outcome, such that one of these actions, for example, gives us a large monetary reward of $1,000, then we should kind of squish our distribution around that action such that that action happens more often. So we'll push this action up, we'll make this a bit higher, and we'll make this a bit lower, and we'll make all of these also a bit lower as well, and this one as well. So we'll go and do it like this. And so the result is this was our previous distribution, and this is our new distribution. Previous, new. Here you can see that this action C now has higher probability. So we pushed that up and brought all the other ones down. So more generally, we can use good or bad outcome as a signal for learning. This can be used anytime you have some goodness measure of your neural network output. So when you can't backpropagate or differentiate through the process that takes your output and feeds it somewhere else, instead of using the gradient as we normally do in supervised learning, we can just adjust our behavior in the direction of the reward. And this is the key idea of the reinforce algorithm. It says that if we have something that we cannot differentiate, we use a reward as our signal to help us move the weights instead. So how does reinforce do that? Let's take a look at the reinforce algorithm. This is taken from the reinforcement learning book, like I mentioned before. I'll put the link in the description. It's available for free online. Let's take this step by step. The input to the reinforce algorithm is some policy, pi, right here. So some policy that outputs an action given some state, and it's parameterized by some parameters theta, and it outputs some action A. This could be our neural network. Then we have a step size alpha. For example, this could be a step size for our ADEM optimizer. And this right here is just initializing our neural network weights. Then we just loop over this part forever, right here. So inside our loop, we have our policy to generate the full episode. So from state 0, we use our policy to produce action A0. The environment takes our action and outputs the next state S1 and the next reward R1. We continue this over and over until we get to the terminal state and terminal reward. So notice that so far we haven't done any learning. We just used our policy to generate a trajectory starting at some state S0, going to some state S1, S2, S3, perhaps over here to S4, etc. until we arrive at some terminal state. And all of this is done using our policy pi. So once we have this full episode of experience, we can loop over each time step of the episode right here, and we compute our discounted return. Discounted return is just sum of all the rewards starting from this step k up to the final time step, multiplied by this discount factor gamma, and this discount factor just takes higher and higher powers as we progress into the future. Once we compute our discounted return here for every time step, we multiply it right here by this other quantity right there. And this other thing is the gradient of the log of the policy. In other words, we take the output of our policy right here, compute the log of it, and then compute the gradient. This is what we multiply our g term by. But looking at this and trying to figure out what happens is kind of tricky, so I'd like to get you to focus on two things. First is how to sample an action. Right here, sample an action is the first key thing we want to focus on, and the second is how to evaluate an action. So to get the action, we sample it, meaning we take our state, feed it into our policy right here, and we get a softmax over possible actions. This forms a probability distribution right here. Then we sample an action from this distribution, and as you can see, some actions are more likely to be picked while others are less likely to be picked. Regardless, once we sample our action, we have a concrete action. So in this case, perhaps we sampled the yellow action because it was more likely. Once we have sampled it, we have a concrete action. So in our algorithm, this is done right here. We're constantly sampling an action from this policy, and the action we sample produces a concrete action right here, A, which we can then give to our environment. Next, the other thing I wanted to notice is how we use this action. Yes, one way we use this is right here when we give it to our environment, but this is not what I'm talking about here. What we're interested in is when we use our action right here. But our policy outputs an action, and here it seems to actually take an action as an input. So the first time you look at this, you're confused. Actually, what we're doing here is taking the concrete action that we selected and finding the probability of that action in our distribution. So this is our concrete action we selected, and the probability of selecting it is 0.3, for example. This is called evaluating. Unlike the previous thing we did, which was called sampling, this is called evaluating. But how do we do this in code? This is just showing it in theory. Well, we can use PyTorch to help us sample and evaluate these things. For example, we can use the Categorical class from torch distributions, which takes a list of probabilities and builds a distribution for us. We can then sample this distribution to get our action. Don't forget, this is zero-based indexing, so number 1 here means the second element was chosen because it had the high probability. After we sample from our distribution, we can evaluate a given action using this log prob function. For example, in our case, we sampled action 1. So the probability of that action is 0.9. After we take the log of that, we get negative 0.105. And we can verify that this is the case by taking the log of 0.9. Let's now go through the implementation of reinforce step by step. First, we declare our environment, then our neural network, and then our optimizer. Next, we gather one episode of experience. As you can see, what we're doing here is simply passing our observation to a neural network right here, gating our probability distribution right here, and sampling from it to get our action right here. After that, we use our action to take a step in the environment. As all of this is happening, we store all of the action states and rewards in these arrays. So we're storing the history of things happening. We will need them later. Next, after we collected our one episode of experience, we loop over the rewards in that episode and compute the returns for each time step. So as you can see here, T represents a time step at which we want to compute our discounted return. And this is the discounted return for time step T. So let's say maybe T is like 2. We want to compute discounted return at that time. All we do is we just take rewards starting at that index and then iterate over them and multiply rewards by discount factor gamma to the power of k. And you can see that this k always starts at 0 for every time step. And so at the end of this, we have a bunch of G's. We have G, G1, G2, G3, etc. And so we have our array of discounted returns. After we computed our discounted returns, we iterate over episode again and update our policy at every step. For this, we get our distribution from a neural network right here by using our categorical class from torch, and then use it to evaluate our actions right here. This gives us this log prob term, which we will use to multiply by our discounted return G. And this gives us our loss. Notice that since in reinforce we want to increase this product, but gradient descent wants to decrease it, we need to put a negative sign in front of it. This way, the negative of this will be made larger. We finish by letting our optimizer take a small step in the direction of our policy gradient. Now let's train our neural network and see a demo of a trained version. Here is how we execute a trained policy. We get our initial observation, get the probabilities from our neural network, use it to build our distribution, sample our action, and then supply this action to our environment, and we render it. So here we can see cartwheel balancing. This shows that it has been trained using this algorithm. I hope you enjoyed this video and this point of view. If you're interested in another weird way of backpropagating, check out my other video on Introduction to Neural Ordinary Differential Equations, where differential equations are used as part of a neural network itself. So there you go, that's it. Now you can go and implement your very own little cute reinforce agent. Good luck.